So it seems like there's a difference, probably, I would say, in the health rate of people who smoke versus people who do not smoke. I don't think that is a controversial thing to say at all, that there's probably a health difference. We will reserve judgment on whether or not smoking is beneficial or harmful to your health. But for now, what I'm curious in is if there is a big difference in heart rate. Heart rate for smoking versus heart rate for not smoking. And does smoking affect your heart rate in some way? So I've gone out and I've gotten some random samples of people. I got a random sample of 26 smokers, and they had a mean of 80 beats per minute with a standard deviation of 5. And then I got 32 randomly chosen non-smokers with a mean and standard deviation of 74 and 6, respectively. And the question is there a difference in mean pulse rates? Now, when you read this question originally, you may say, well, of course there's a difference. Smokers are 6 beats per minute higher than non-smokers, which seems like it's about 1 standard deviation higher. If I took a non-smoker's mean and added 1 standard deviation, I'd be at 80. And 1 standard deviation maybe is significant, maybe it's not significant, but what I want to know is, can I prove statistically whether or not it is significant, and if it's significant, how much? So I'm going to perform a hypothesis test, and this is going to be a little different from other hypothesis tests in that I'm comparing 2 different groups to each other. Now, this is different from, say, a one sample t-test or a one proportion z-test, where I was comparing what actually happened in my population to what I expected was going to happen. Here, I don't have anything that I expect to happen. I'm just comparing these 2 groups to each other. I don't know what the average resting heart rate of everybody would be if I combined smokers and non-smokers, and for the purposes of this hypothesis test, I don't want to combine smokers and non-smokers. I want to specifically compare these 2 groups and see how different they are from each other. Now, the reason I'm giving you that long of an introduction is because writing these hypotheses can be a little bit tricky. So when I write the null hypothesis, what I want to know is the average heart rate of smokers different from the average heart rate of non-smokers? And the null hypothesis, as with all null hypotheses, is no, of course not. There is no difference. The average heart rate of a smoker is equal to the average heart rate of a non-smoker. So I'm going to write this in kind of an unusual way. I'm going to do the average of a smoker minus the average of a non-smoker is 0. There is no difference between the 2. Now, if you wrote the average of a smoker equals the average of a non-smoker, that is exactly the same thing. You're welcome to write that, but I like to write them as a difference because of the way that we're going to write our t-score calculation. You'll see that in a minute. So let's write our alternative. Our alternative, I'm going to go ahead and say, is that they are different. So that the average heart rate of a smoker minus the average heart rate of a non-smoker does not equal 0, meaning they are not the same. I'm not making a judgment at this point on whether smokers are higher or non-smokers are higher. I'm just curious if they're different. Now, my data indicates that smokers are higher, so that might also be a reasonable test, but I'm just testing if they're different. Maybe I have reason to think smoking lowers your heart rate. Maybe smoking reduces stress, and so your heart rate's lower. I don't know at this point, so I'm just going to play it safe and do a hypothesis test as they're not the same. So there are some conditions that I need to check. First of all, I need to make sure these samples are random, and of course I know they are because I've told you right here that they're a random sample. I believe that they are independent samples, meaning I used good statistical practices whenever I selected these people. If I've got 26 smokers and 32 non-smokers, I think it is certainly safe to say that I meet the 10% condition, because 32 is less than 10% of all non-smokers, certainly, and of course 26 is less than 10% of all smokers. And then I would have to check the nearly normal condition to make sure that whenever I plotted these, they were approximately normal, but I don't need to because I'm told right here in the problem that both sets of data are roughly unimodal and symmetric, which means that I meet the nearly normal condition. So I need to go ahead and say this. I have independent random samples. And I want to say that each is less than 10% of the population. Now, I need to specify that each one of these is less than 10% rather than, the total number of people, what is it, 58 people is less than 10% of the population. I need to make sure I have less than 10% of smokers and less than 10% of non-smokers. Both groups have to meet the 10% condition. And the data is approximately normal, because the problem told me the data is approximately normal. So I'm going to perform, and this is important, you need to say that, you need to write out what the test is you're going to do. I will perform a 2-sample t-test. Now, a 1-sample t-test is used if I'm comparing a group to what I expect the group to have. A 2-sample t-test is when I'm comparing two groups to each other. Okay, so let's go ahead and work it out. Let's do let's get the mechanics here written out. First of all, the number of smokers I have is 26 according to the problem. The average, which I will write as y bar, the average of my sample is 80. And then the standard deviation of my smokers, I'm told, is 5. Now you may be wondering, why did you use this symbol up here for mean, the average smokers, and why did you use y bar down here for this average? And the reason is that this symbol means the average of the whole population. This is I want to say mu, maybe it's a Greek symbol. This is the symbol for the average of the entire population. I have no idea what the average of the entire population is because I didn't ask everybody. I only asked 26 and 32 people in each group. So I have no idea what this is, but I'm saying that I think the average of the populations is going to be the same. Here, this y bar is the average of my sample, and that I do know because I went and asked them. I collected that data. 80 is the average of my sample. So this is the population which I rarely, if ever, will know. And this is my sample. That's the number I'm going to use to estimate the population. But the notation just means this one I went and counted myself. This is my sample. This is the whole group. Okay, and then of course for my other group, the number of non-smokers was 32. And the problem tells me that the average for non-smokers was 74, and that the standard deviation for non-smokers was 6. I'm using S and NS for smokers and non-smokers. You can use whatever symbols you like as long as you can keep them straight, which is which. I could use S and N or X and Y. I mean, it really doesn't matter as long as you specify which is which. Okay, so I'm going to go ahead and perform a t-test. I want to go ahead and do what did happen minus what should have happened over the standard deviation. So here's one of the reasons that I wrote these as differences. On the top, I'm going to write what the difference actually was. Well, the difference between smokers and non-smokers was 80 minus 74, which is 6. I'm going to write it out as 80 minus 74, but that 6 is what the difference actually was, minus what I thought the difference was going to be, or what I think the difference should be, which is 0. Over the standard deviation. Now here's where we get tricky because I have two different standard deviations at work here. Now I'm going to refresh your memory real quick for the standard deviation of a population. That is the standard deviation of my sample over the square root of the number of people in my sample. And if I was only using one group, this would be perfectly fine, but I'm not. I'm using two groups. I'm using smokers and I'm using non-smokers, which means I will have two different standard deviations to add together. I will have the standard deviation of group 1, let's go ahead and do like S, the standard deviation of my smokers plus the standard deviation of my non-smokers, and hopefully you have some warning sounds going off in your head right now whenever I write this, because I'm not allowed to add standard deviations. I can't put these together. What I can do is add the variances. So I would need to get the variances for these first, so square the standard deviations, add those, and then square root the whole thing. So here's what that ends up looking like. On the bottom here, let's just go ahead and do the square root. I've got the top, which is my SD of my smokers squared, and the SD of my smokers was 5, so that's going to be 5 squared on the top. And on the bottom, I'm going to have the square root of 26, because that was how many was in my sample, the square root of 26 squared. Now if you have a square root squared, that just means the square root drops out and I just have 26. Plus, non-smokers had a standard deviation of 6, so that'll be 6 squared, over the square root of 32 squared, which is 32. So this is the variance for my smokers. This is the variance for my non-smokers. I add the variances and then square root them. Okay, so once I get this written out, I could perform these calculations, but I'm really going to go ahead and let the calculator do it for me. And the reason I'm going to let the calculator do it for me is for a couple of reasons. But the biggest one is that whenever I work this out, and spoiler alert, here's the answer, it's 4.15. 4.15 does not appear on my z-score chart. You might have one that goes that high. I do not. Mine only goes to 3.49. Mine doesn't go all the way up to 4.15. So I'm going to use the calculator to get a really accurate answer. Some of you may just say, well, you know, it's more than this or it's less than this, but I can get a lot more specific if I do the calculator. The second reason I want to use the calculator is because this is a two-tailed test, because it was not equal to, and two-tailed tests are somewhat difficult to calculate sometimes. It's easy to mess up adding the two tails together. So the first thing I'm going to do is just go ahead and clear out what I had here before. And if you, I'm on a TI Inspire. Of course, you can do this on any calculator, but it's easiest on the Inspires. I'm going to go down to statistics, and I'm going to do a stat test, because this is a hypothesis test. Oops. And the hypothesis test that I'm doing is a t-test, but it is a two-sample t-test. And you'll notice there's an option right here for the two-sample t-test that I will select. The data input method is not going to be data. Data would be if I had a list of numbers. I don't have a list of numbers. I was given the actual statistics. So I'm going to select stats. And then I've got a place where I can put everything in. The first is the average of my first group, which was smokers. And the average of smokers was 80, so let's put in 80 there. The standard deviation was 5, and the size of the sample was 26. Okay, now let's put in the data for the second group, which was an average of 74, a standard deviation of 6, and the number of things in the sample was 32. And then I'll tab down to the hypothesis. By default, it is that the hypotheses are not equal to each other, which is what my hypothesis was, not equal to each other, so I'm going to leave that alone. Pooled, I suggest leaving it no. It's not going to make a huge difference if you pool it or not, but I'm going to leave it as no. I'll explain why a little later. Let's go ahead and go to OK. And here you'll notice it gives me a lot of information I already knew. It gives me the averages, the standard deviations, and the number. Of course, I already knew those because I put them in. But up here at the top is the good stuff. There's my 4.15, which is what I already told you the answer that was going to be, 4.15. But then it gives me the p-value and the degrees of freedom. So that's what I'm going to write down. I'm going to write down the p-value is, and I'm just going to round this to 4 decimals, 0.0001. And the degrees of freedom was 55.953. Right here, 55.953. It's okay to leave that as a decimal, but I'm going to go ahead and round it to 56. Not that big of a deal either way. Now what I want you to notice is that in this particular case I had 58 total things in my sample. Remember I had 26 smokers and 32 non-smokers. That's 58 things. And so you would expect, since degrees of freedom was 1 minus, the sample size minus 1, that I would have 56, which I do when I round. When I round, I have 56. But the calculator doesn't give me 56. It gives me 55.953. Calculating degrees of freedom for two sample tests is a little more tricky than just subtracting one from both sample sizes. There's a pretty major calculation involved to get that number. The calculator's not being goofy. It really is 55.953. That's why I suggest you use the calculator for it. It's not always just a matter of subtracting one with a two-sample test. With a one-sample test, subtract one, you're fine. With a two-sample test, it's a little more complicated, and it's not the kind of thing we really want to get into. So just take the calculator's word for it, 56 degrees of freedom. Now, let's talk about what this p-value means. I would certainly classify this by any standard as being a low p-value. So, because the p-value is small, I reject the null hypothesis. There is strong evidence of a difference Remember, I did not test whether it was greater than or less than. I just tested if there was a difference. There's a difference in mean pulse rates for smokers and non-smokers. So I've answered the first part of the question. If we come back to the problem, the first part of the question was, is there evidence of a difference? And I'd say the answer is yes. There is evidence that there is a difference. The second part of the question, how big? How big is the difference? And to answer that question, I'm going to go ahead and do a confidence interval. Remember, confidence intervals and hypothesis tests go hand in hand, so let's go ahead and do one of those. And I'm going to show you the notation. This is not that important, but just so you see what it looks like. The difference between mean for smokers and non-smokers, plus or minus the margin of error. Now the margin of error, remember, is the critical value times the standard error. And the critical value here is the t critical value for 56 degrees of freedom. Remember, I rounded to 56. Another reason that we rounded, because our chart is not going to show us 55.9 degrees of freedom. The chart will only show us whole numbers. Okay, so times the standard error of that difference, the average smokers minus the average non-smokers. Okay, this is all well and good, but let's show what it actually looks like. The difference was 80 minus 74, of course, plus or minus. I'm not even going to put a number in here because I'm going to have the calculator do that for me, so I'm just going to leave it as critical value for 56 degrees of freedom, times the standard error. Standard error shouldn't surprise you at all what that looks like. We just used it a second ago. It's the square root of the variance of group 1 plus the variance of group 2. No surprise there. Equals, okay, and now I'm going to have the calculator do the rest of the heavy lifting for me. So back to the calculator. This time, whenever I go to my statistics menu, I'm going to select confidence intervals, and I want a 2-sample t interval. The data input method is stats again. I don't have a list of data. Okay, so the average of the first group was 80 with a standard deviation of 5 and a size of 26. The second group was 74 with a standard deviation of 6 and a size of 32. And let's do 95% confidence, I guess is fine. Again, we're going to leave pooled as no for now. And here we go. It gives me some information I don't necessarily care about, but then it also gives me the lower and upper intervals, which is 3.12 and 8.89. So that will be my interval. 3.12 to 8.89, which means what? I am 95% confident that the mean pulse rate for smokers, remember I was doing smokers minus non-smokers, and my confidence interval gave me all positive numbers. Smokers minus non-smokers being positive means smokers is higher, is between 3.12 and 8.29 beats per minute higher than non-smokers. So I answered the two questions that I needed to answer in this problem. First, I answered the question, is there a big difference between them? The hypothesis test told me yes, there is. And then, how big is the difference? I'm 95% confident that the difference between the two, the true difference in their averages between 3.12 and 8.89, again, strong evidence that there is a difference in resting pulse rates between smokers and non-smokers. Okay, so that is a 2-sample t-test and a 2-sample t-interval.